Good morning, boys and girls, and welcome back to part 2 of slope field and Euler's method, where we're going to deal with the Euler's method part of thing, or Euler's method. I prefer the pronunciation Euler's, but I think you hear it both ways. All right, named after the great mathematician Leonhard Euler. If you don't know about this guy, you should go read up on his life's history. It's actually quite entertaining. There's a great book if you want to read about some mathematicians, Of Men and Numbers. It's a good little read about the history of some famous mathematicians. But today we're gonna deal with Euler's method, and Euler's method is a tangent line approximation. And so let's go back to our good old friend GeoGebra, and let me give you a little demonstration of what Euler's method does or is. Okay, so here is basically the long story short with Euler's method. All right. Earlier on we talked about tangent line approximations and how, if you look closely at a graph, locally it is linear. It doesn't matter how curved it is. If you get real close to it, locally it's linear. And we said so the tangent line was a very good approximation of the function if you were very close to the point of tangency. Okay. Our issue was, as I get farther away from my point of tangency, right, I get further away from my graph, and therefore then it becomes a worse method to use to approximate the function the farther away you get from that point of tangency. So Euler's method tries to address that problem and says, well, let me just use this tangent line and let's go out some distance. And then once I get out some distance, let me find the tangent line of the function at that point. All right, I wish I could draw on this here for you guys, but I'm not able to. And then, now let me use this new tangent line here. And then I'm going to go out some distance. Okay, we usually go a consistent distance. And then let me find the tangent line at that point there. And I'm going to use that tangent line now. And then let me go out some other distance, and then I'm going to use that one. And you can see, so what we've done here is we've used, 4 different tangent lines, okay, with n of 4. And you can see that, if I would have just followed this first tangent line the whole way, I would have been way off by the time I got over here to what I'm trying to approximate. I mean, my approximation would have been horrible. But if I split it up and I use a bunch of different tangent lines, if I keep adjusting my approximation, then my approximation ends up being, not too bad, or at least a little bit closer. And ways we can improve this is if I do more, instead of just doing 4 tangent lines, if I increase the number of tangent lines I'm going to use to get me there, right? If I increase that n value, now my approximation gets closer and closer to what the real thing is. And you can say, hey, that's actually not too bad if I, did 20 tangent lines for this function. Or I guess if I also moved it closer, but that's basically what Euler's method is doing, is we are, approximating, adjusting our tangent line, approximating, adjusting our tangent line, approximating, adjusting our tangent line, approximating. And so when we kind of go through the steps, I think it helps to have this picture in mind of what we are trying to do, or what we're trying to accomplish when we do Euler's method. Okay? I'm not going to lie, as we jump into it here, it's going to be a bit of work. Okay? Mostly these are calculator questions, though, so you'll see I'm going to use a lot of calculator here, or they're very short if you are not able to use a calculator. The one that we're going to do now is probably worse than any you will ever see on an AP exam. All right? But we're going to try to just get this process across. All right, so let's go back to our notes here now. Okay, so going back to our notes now, you are generally going to use Euler's method when, again, you don't have the original function to evaluate, right? It's too hard to get the original function. All I have is I can measure its rate of change of something, and so I just get the differential equation, or I just have the derivative. That's all I'm kind of given. I have maybe a starting point. I know where I'm going to start, and then I have some place that I want to get to. So they might tell you what to estimate and tell you how many steps to use. They might say, hey, use, again, n is the number of steps. They might say, hey, use 6 steps. And they might tell you your h, or your step size, or your delta x. Okay? These are all different things that could represent right there. All right? Now, if you look in the book has got like an equation that kind of sets this up. And again, it's doing the same thing that we're doing here. I've always learned this from a table. You need to show your work somehow, though, some way. Okay, if you want to use, if you like the equation from the book, you can go ahead and use that instead. But I've always done that using this table here, where, again, I've got my point that I'm starting from. I'm going to use my derivative, which in this case is x plus y. And I'm going to use that to get the slope of the tangent line, right? Then I'm going to find the change in the y value by using the derivative and my change in x value. And then I can find a new y value on my new point by adding the change in the y value to the old y value. That's what this table is set up and what it's doing, right? So we have some original point. In this case, we're starting out at the point 0, 2, all right? And then I'm going to work through this process. And again, I don't think this is really hard. It's more kind of tedious, all right? Then I'm going to find my change in y. So y prime equals the x value, which in this case is 0, plus the y value, which is 2. So that equals my delta y in this case is 2. All right. Then I need to now go find my change in y. The change in y is going to be, again, your y prime, okay, your derivative. So in this case, 2 we found in this last step over here, times that delta x. And again, delta x is the same thing as the h value, okay? It's that step that we're moving over on the x-axis. So in this case, 0.05, all right? And so I'm going to multiply those together, and we get 0.1. Okay, so my delta y, my change in y, from one point I've gone over 0.05, and now I'm saying I'm going to go up 0.1. So now I can go find my new y value, which is the old y value, which the old y value was at 2, plus the new y value, which is 0.1. And so now my new y value is 2.1. Okay, so that next point now that we've gone over, on the x-axis, we said we just went over 0.05. And on the y-axis, we are now at 2.1. And now I want to go and estimate my next point, and I'm going to follow this process all over again. Okay, so here is our next step now. I found my y prime, which was, again, x plus y. So now I'm going to use the new point, 0.05, 2.1. So 0.05 plus 2.1 gives me 2.15. Then I got to find my new delta y, which I'm going to take the y prime I just found, 2.15, times, using my thing, I don't know if I was doing it, 2.15 times, again, the delta x of 0.05, and I get a new delta y of 0.1075. All right, and now I'm going to find my new y. So I take the old y from the beginning of the problem, 2.1, and then I'm going to add that new delta y, 0.1075, and so now I get a new y of 2.075. Okay? So again, what we did is we used, one tangent line, estimate a new point. Now what this is doing is using that new tangent line, basically, and finding a new, better approximated point. And now, again, I'm going to keep doing this. I'm going to keep adjusting as I go. All right? This now gives me another new point of, now we're at, so I've got to add 0.05 to the other one because we moved over that much again. So now I'm at 0.1, comma, and my new y is 2.207. And now you can, I would say you can truncate or round in your work. However, on your calculator, I'd be carrying this whole number all the way through. Okay, and generally, again, this is a lot of calculator stuff. I'm going to pull up my calculator thing for this next part. This program's kind of just been doing the math for me, so I've been letting it. I'll pull the calculator so you can see next on these next steps. But basically, I'm just going to keep going through the same process over and over again. So again, that's why I don't think it's too hard, but it is, it is a bit tedious. And normally, on an AP test, they only make you do it 2 or 3 times. I've never seen you do it like we're doing it 6 times here with 6 steps. I've never seen them go that far. But hopefully you kind of get the idea of how this kind of works now. Okay, so here's how normally it's going to look is, again, I'm going to just do things on my calculator. So to find y prime, I take the x value, 0.1, plus the y value, 2.2075. Again, use the whole thing. And I'm going to get my answer. Oh, it's under my picture. I can't hit enter. Sorry. Hit enter. And so I get my answer. All right, so now we found our y prime, right, is 2.3075. And so now to find the delta y, we said we need to take our y prime, so this, and I just hit, so answer times, and I need to multiply it by 0.05. Oh, calculator. 0.05, 0.05. That's why I normally try to do stuff not on the live stream here. And so again, there is my new delta y now. So when you do this again, you might truncate on your table on your work. And again, when you set up this table, you need to tell people what you're doing in the table. And these first few steps, I showed you what I was doing. But generally, you can just say, hey, y prime is this, delta y is this. As long as you tell people up above, you know, how you came up with those numbers. Okay? If you told them what you did to get that. But you can truncate on your table. But again, in the calculator, I'm going to continue to use this whole big number. Now I need to find my new y. And so again, to find the new y, sorry about the bell. Now to find the new y, what we're going to do is we're going to take our old y. Our old y was this 2.2075 plus, and I just grabbed the answer from up here, that delta y, and so we get 2.3228. Okay, so now you can see when we go and get that new y, you should get like 2.3228, and then I could take that, oh, maybe, I don't know if we can see that on my calculator down here, but maybe there you can see it now. I take, can't remember, I got interrupted, so I can't remember if I talked about this, but I got the old y plus that delta y, so there's my new y. Again, I might round it in my problem. I can write my new point now with that to continue on with. But again, continue to use the whole numbers in your calculator. I'm going to go ahead and complete the table here, and you should maybe pause the video and try to do the next few rows on your own, and then you can kind of quickly check your answers. And again, your answers should be accurate to mine. Okay? You want to keep using the whole numbers, otherwise you're going to get off and you're going to get rounding error in these things, and that's something that we don't want. Okay, so check out the rest of your table here. It should look something like this with these points, and you can look at all your values for y primes and delta y's and new y's. Again, each time as you do this, you can truncate answers in your table. Really, your table could look at the bottom part of my table, but the top, I'd better tell people how you came up with stuff. Tell people you're using the point, the derivative, that you're coming up with delta y and the new old y. This is really the only part you have to memorize, you know, that top row, in order to do Euler's method. Once you have that memorized, then it's just kind of cranking through this process every time. It's tough, and it reminds me of a line from when I first did the videos. When I see Euler's method, I skip it because it's wretched. Okay, was one of the parody quotes they use. It is a hassle. I mean, it's kind of a thing, but I don't think it's super tough once you kind of get it down. All right, but summing this all up now, you know, my answer now, my last final point would be 0.3, 2.720. And so what we're saying is that, hey, if I were to plug 0.3 into the y function, whatever that is going to be approximately 2.720. That is my approximation. Okay? And so Euler's method, again, allows me to approximate better what is going on, you know, when I'm trying to approximate something farther away from the point of tangency, from that initial point of tangency. All right, boys and girls, I hope this made some sense. If you need help, again, come find me. Otherwise, see you later. Have a great day.